what we've said is Farhan determined that the magnetic field that's in red will affect the amount of magnetic force. Sienna said that if the particle is moving faster, then because of that, it would produce a stronger magnetic field, which would produce a stronger magnetic force. When I say it would produce a stronger magnetic field, I mean the little itty-bitty magnetic field that's around the charge, not the red one, the other one. And I've given you a minute here to think about what the third thing might be. Does anybody have it? Evan? The charge. This goes back, and it's not really intuitive because I've told you that there are two things necessary for magnetism. Remember, for gravity, you need mass. For electrical forces, you need charge. The two things you need for magnetic forces are charge and motion. So it's no surprise that both the motion and the charge determine the amount of magnetic force. In fact, I'll show that to you in a different way in a second. But basically, the charge on the particle, not sure why that is like that. Oh, I see. The speed of the particle and the strength of the magnetic field that the particle is moving through. And it's both the charge on the particle and the speed of the particle that determine the little tiny circular magnetic field that the particle is carrying around with it. So now, that's all kind of an intuitive thing. But let me show you mathematically what's going to happen here. Give you a second to finish jotting that down. And we're asked to come up with a formula. Right? There's a box there. We're going to put a formula in. But check this out. If I talk about a gravitational force, these are all forces. I've told you that to calculate the magnitude of the gravitational force, you take the property of matter responsible for gravity, mass, and you multiply by the associated field, which would be gravitational field, right? And I've said by way of a comparison, that's why if you talk about an electrical force, the magnitude of the electrical force is found by taking the property of matter responsible for electric forces, which is charge, and multiplying by the associated field. Does that make sense? Are you following my drift here? Okay. So how do we go about calculating a magnetic force? Well, I'll stay over here actually. The magnetic force, I'm just going to put it below because I don't really have a lot of room up here, would be the property of matter times the field. Well, the magnetic field is B, but the property of matter responsible for giving rise to magnetism is two properties. It's charge and speed. And that means that you can calculate the magnitude of the magnetic force by multiplying these three things together. It's more complicated than that a little bit. Let me show you the formula as it would appear on your formula sheet, and then you can add to what you've just written. But before I do, property of matter, M times gravitational field strength. Property of matter, charge times electric field strength. Properties of matter, QVB, so that's QV are the properties, times magnetic field strength. This is what the formula actually looks like. There is a perpendicular symbol as a subscript to V. And that's on your formula sheet, by the way. It's under electricity and magnetism. right here. Pretty much the bottom of the screen here in the middle. So Fm equals QVB. There's some other formulas, we'll get to those later. What is the deal with the perpendicular symbol? The perpendicular symbol means the velocity that you use in that formula is the part of the object's velocity that's perpendicular to the field. So, what does that mean? Well, that means that if you had a situation where you have a magnetic field this way, and the object is moving this way, then V perpendicular is 0. No part of that motion is perpendicular to the direction of the magnetic field. That would mean there's no magnetic force. Whereas a particle moving this way with a certain velocity, the perpendicular component equals the entire speed, because the entire vector that's the velocity vector is perpendicular to the magnetic field. If I had a third particle moving with the same speed as the other two, but it were moving in that direction, it would experience a magnetic force because there is a perpendicular component to that velocity. But it's not the entire velocity vector. Okay. So we're going to look at a few examples here. The first few have really nothing to do with that perpendicular nature. Example 1 says, what's the magnitude of the magnetic force on an electron traveling with that speed through a magnetic field? And that's an amazingly strong magnetic field, 4.20 Tesla. Well, the formula is Fm equals QVB. I will almost always just write this. I don't have time in my life to put perpendicular all the time. But I want you to notice that nothing about this formula will ever give you a direction. You can't get a negative out and say, oh, it's south. How do you determine the direction? Use the right-hand rule if you want to. So all we have to do is multiply three things together here. We're going to multiply the charge of the electron by the speed, which is 3.6 times 10 to the 4 meters per second. Okay, so let's take a look at example 2. Calculate the upward acceleration of an electron that's traveling east at a particular speed. Let's just stop for a second and check something out. If an electron were traveling east through a magnetic field that is south, would it be accelerating up? So if I were to use my right-hand rule and I have an electron that's traveling south, so if we're looking at a map, south is towards the bottom of the page, and it's traveling east, east is towards the right side of the page, which way would it be forced? It would be forced out of the back of your hand, which is away from the surface of the Earth. That's true. Okay. So what is the upward acceleration? Well, what you should note is that whenever we find acceleration, we've done this many times before, you're always going to be looking at net force in relation to the mass. And in this particular case, the force is a magnetic force. Now be careful there. We have two m's. We have two m's. The m on the bottom stands for mass. The m on the top is magnetic. So how do we calculate the magnetic force? Well, that's pretty easy. That's QVB. So the acceleration will have a magnitude of QVB over m. And that's all we need to do here. You need to take the charge of the alpha particle. Be careful because it is, or sorry, it's not an alpha particle, it's an electron. The charge of an electron times the speed that it's moving at times the magnetic field divided by the mass. And by the way, in this question, just like question 1, this speed that we're using, it's the perpendicular speed because the particle is moving east through a magnetic field that is south. Everything's perpendicular. Let's see, we have 1.6 multiplied by 10 to the negative 19. I'm going to multiply by the speed, which is 8.3 times 10 to the 4. And then we have to multiply by the magnetic field strength of 0.31 and divide by the mass of 9.11 times 10 to the negative 31. Just double check my entries. I think they're okay. So I get 4.5 times 10 to the 15 meters per second squared. Getting the same result? Okay. So no great shakes so far with this stuff. The only thing we're doing with this example is we're equating the net force with the magnetic force. So the answer is 4.5 multiplied by 10 to the 15 meters per second squared. Take a look at number 3. A carbon ion is moving in the direction indicated through a magnetic field. We're given the magnetic field strength, you're given the charge of the carbon ion, and you're given the mass of the carbon ion. And you're asked, how fast does this ion have to move so that it's not deflected? Look, if this particle is deflected, it could be deflected because of a magnetic force. Let's find the direction of the magnetic force using the right-hand rule. So I would like everybody to use the right-hand rule. This is going to be very similar to the question that Shesmaida asked about, where very similar, where we had this situation. It might even be identical. I don't know. Okay? But I want you to figure out the direction of the magnetic force on the alpha particle. I keep saying alpha particle. On the carbon ion, and it's positive, as it moves through those two poles. Towards the top of the page, I hope. Fingers north to south, thumb in. It's a positive particle, so it's forced towards the top of the page. Are you with me on that? Okay. So, is it possible that it's not forced up? Is it possible that this particle, when it goes in, goes down? Is that possible? tell you the answer to that question is yes. My question to you then is, how would it be possible if the magnetic force is up, which it is, how would it be possible that the ion is deflected down? And by the way, before I get to your answer, Liam, I don't mean to suggest that it goes in and straight down, but it curves down, right? Or maybe it curves up, or maybe it goes straight through. How is it like you're flipping a coin, Liam? Right. Gravity is involved here, and you're going to take gravity into account. This is my take on it. When you see a question on an exam and you're told the mass of the particle and it has to do with forces, then we're going to include gravitational forces. So what we have is a gravitational force that is down. We have a magnetic force that is up in this question. And the question is basically, well, I don't want to really give it away, but I guess I will. Do you see that if those two forces are equal in magnitude, then it will go through undeflected? Right? So the idea here, and what I'm about to explain, is just as important as getting an answer to this question. The idea here is that if it's undeflected, then what that means is F net is 0. The net force is 0. And the only way the net force to be 0 when you have these two forces that are in opposite directions is if the magnetic force, well, I'm going to write something down here. Is this a true statement that I've just written? And you people in Physics 20 that I had, you should know the answer to that is no. Why is this not true, Farhan? Right. These two forces are not equal because one's up and one's down. However, the magnitudes are equal. So I want to go back. This force analysis, like I said, is just as important as getting the answer. We have F equals F here, right? Basically. If I go back and I look at this question, do you see I could have said F net equals Fm? Is this true? That's interesting. Is this true? No, sorry. Is that still true? That's true. The net force equals the magnetic force because it's the same force. This you may go, oh man, this is being really picky, but it's important. These two forces can be written as equal to each other because you know what? There is only one force, and I can call it a net force or I can call it a magnetic force. These two are equal because there's just one force described two different ways. These two forces are equal, and if you're watching this on video, I just put air quotes around the word equal. These two forces are equal only in magnitude because you know what? There are actually two different forces that are in opposite directions that cancel each other out. And there's a real important difference between that. You have to have absolute value signs here. Bottom line, though, is we end up with this. QVB equals mg. This right here is the physics. This formula of Fm equals Fg, the absolute value signs, that's the physics. The rest is just going to a formula sheet and then putting numbers in. So V will be equal to mg over QB. And you know when we write electric field strength with an E, I say no, put those absolute value signs, put that vector symbol. I don't do that with B. There's nothing else that B is used for in physics. So when you see a B, it's magnetic field. Let's throw all of the numbers into that, toss it around and see what our calculator spits out. We have the mass, which is 2.01, multiplied by 10 to the negative 26 kilograms, times 9.81 newtons per kilogram. over the charge of the carbon ion, which is this number. You only know that's the charge, everybody, because you were told that's the charge, right? It's not something you have to memorize. And times the magnetic field, I don't even know if I looked at it. 6.32 times 10 to the negative 5 Tesla. That's suspiciously close to the magnetic field of the Earth. And the magnetic field of the Earth is very weak, which means the magnetic force is probably going to be pretty weak as well in this situation. Mind you, we're comparing gravity and magnetism, so I'm not so sure what we're going to get for a speed. I have a feeling it's going to be kind of a slow speed. 2.01 times 10 to the negative 26 multiplied by 9.81. We need to divide that by 1.6 multiplied by 10 to the negative 19. We also need to divide it by 6.32 times 10 to the negative 5. Again, we've had this conversation, I'm sure. I just divide by them both. If you want to divide by the product, then you need a set of brackets, and then you multiply them inside of the brackets. Looks good. So yeah, 1.9 centimeters per second, or 1.9 multiplied by 10 to the negative 2 meters per second. You're getting the same number though. Is that right, Dua? So nothing really that challenging so far. And in fact, the next question is not that challenging either. It just takes into account an angle. Tomorrow we'll start to get into more in-depth analyses of what's going on. Sorry, I was just checking my sound. A proton is traveling at this direction indicated. Now I want to stop you here. You remember when Shazmaida asked the question, and I was talking about we have a three-dimensional situation on paper, and sometimes lines are drawn at weird angles to indicate in or out? That's not what this is. This literally means it's traveling in this direction along the paper. Okay? It's not traveling in. It's in the same plane as the magnetic field. And what we are asked to determine is, I don't even have the question here. Correct me if I'm wrong. It says, what's the magnetic force? Okay. So we're going to use the formula QVB, except we have to now pay attention to that perpendicular symbol. So we need to calculate or figure out how much of the velocity is perpendicular to the magnetic field. When you take a look at this particle's motion, it's moving not in the same direction as the magnetic field, but it's not moving entirely perpendicular to it either. It has a horizontal component and it has a vertical component. This is what you need to figure out in order to determine the force. This number right here is the hypotenuse of this vector diagram with the components. So it's not a difficult calculation. You're going to take, well, we can write sine of 50 degrees equals the opposite side, which is v perpendicular, over the hypotenuse, which is 5.8 times 10 to the 4. Get this, and then throw it into the formula with the charge in the field. That's it. Yeah. Yours is to the 5. Thank you. Let's go with what you have. That way I don't have to worry about you changing anything on paper. I'll just change mine up here. So this is times 10 to the 5. Can't be right. So obviously I'm in radians. And luckily, being in the wrong mode gave me a number that told me right away it was wrong. But be careful because sometimes you get a number that looks like it might be okay. Let's do that again. 4.44 times 10 to the 5 meters per second. Anybody else up for that number? Okay. So that means we're going to have the charge. What is it? Proton 1.6 multiplied by 10 to the negative 19 coulombs. I don't know why I'm putting all the units today because you know me, I normally don't worry too much about them. But then we have that 4.44 times 10 to the 5. Oh man. Meters per second. And then the magnetic field of 8.3. Milli means 10 to the negative 3 Tesla. And that's it. So I have the charge times the speed that I got times the magnetic field strength, which gives me 5.9 times 10 to the negative 16 newtons. Good with that one? Okay. So we have this right-hand rule. If you need to use it in any of these 10 questions, that's what you would use to determine the direction. But the new thing today is how do we determine the actual force? And it's with this formula, F equals QVB. Tomorrow we're going to just extend this and, like I said, go a little bit deeper in terms of what's going on in the behavior of charged particles. But in the meantime, you've got 10 questions to do. You've got lots of time to do it in. Well, I don't know. You got about 20 minutes or so, I think. 15 minutes, roughly. Remember, if you need to leave for some reason, that's okay, of course. And I'll come around and I'll check on you and see how you're doing with this stuff and how everything's going.